Hi, we defined the sets of numbers, and now it's time to define some operations that can be applied between the numbers, the elements of the sets. Okay, we will consider now the set of real numbers, and we'll define operations on these real numbers. First, we define the first operation, which is the addition, denoted plus, and then the multiplication, denoted by times. Now, you might ask yourself, why do we need to define plus and times? We already know all this. In fact, when we are doing mathematics properly, we have to define everything. And when we say we want to define, we define what does it mean, what this operation will give, and then we need to define what are the properties, or study the properties associated to each one of these operations. When you will study another course, which is the algebra, you will find out that these operations can be defined in many different ways, in many different sets. So you can have a set of, I don't know, a set of elements, which are elements that can be food, like a cake and a chocolate bar and an apple and a banana. And then you define like a plus of two elements when you mix two elements together, or a plus or two elements when you do something else. I don't know. So we define any operation between elements of a set, and then after defining these operations, you can deal with the elements according to these operations. So let's say, for example, if you mix a banana and an apple in a mixer, that means you did an addition. If we define the addition as mixing in the mixer, then of course mixing a banana plus an apple is equivalent to mixing the apple plus the banana. So this addition of apples plus bananas is commutative. So you can exchange the order of addition. So this addition as defined is commutative. And this is how we'll do things. So now we'll take the most natural definition that you already know of plus and times. And later in algebra, you will find out how to define this kind of binary operations. We call them binary operations. So we define now the addition and the multiplication of two elements in R, and these addition and multiplications are defined as being internal laws. Internal laws, it means that when you add two numbers, the result will be a number. When you do the addition between two numbers, the result will be a number in R. So it's internal. Okay, when you multiply two numbers, the result will be an element in R, not outside the set R. So these are internal laws. So they stay in the set where they already belong. So what are the properties of the addition that you know and the multiplication that you know? The addition means that you are taking these elements and adding to them the other elements. So if you are adding 2 plus 3, it means that it's 1 and 1, and then 1 and 1 and 1. And if you, the multiplication is defined as being, if you take x times y, it means that you are adding x, y times, let's say. Okay, so this addition and multiplication have the following properties. Between parentheses, I would like to say that this part of the chapter is put in here so the chapter can be complete as it should be, but it's not the main objective of our work, because this is something that you will do in details in algebra. So here it's put only to complete the chapter, and so the course can be not missing anything else, okay, anything important. So first, plus is associative. It means that if you add two numbers and then you add a third one, it's the same as adding the second and the third and then the first one. It's commutative. It means that if you add two numbers, a plus b, it's the same as adding them in the different order, b plus a. Also, when you define the addition and the multiplication, first the addition in this case, we would like to look for a neutral element. Okay, what's a neutral element? It's an element that if you add it to another element, it will not change it. So x plus this element will be x. And in this case, it's the number 0. So the real number 0 is the neutral element, and it's neutral whether you add it on the right side or on the left side, because the law plus is commutative. So x plus 0 or 0 plus x is equal to x. Also, we would like to find if x has an opposite, which is the case. Opposite number, it means it's a number that if you add it to the original number, the result will be 0. And that's also true because any number, any real number, you can add to minus itself, it will give 0. And on both sides also because the law is commutative. So this is the structure of R equipped with the plus law or the binary operation plus. It has all these properties. Now for the times, we can notice that times is associative as well and commutative. So we have similar properties as in plus. We have also a neutral element, which is 1, because 1, if you multiply it by any other element in R, it will give an element, the same element in R. So a times 1 is equal to 1 times a equal a. And also any real number has an inverse element. So if you take x and you multiply it by 1 over x, which is a real number, you will have 1, which is the neutral element. So we were able to find a real number that we multiply by x to have the neutral element. That it means that any real number has an inverse, which was the opposite for plus. Okay, the opposite number in there. And finally, times is distributive with respect to plus, which means that a times b plus c is equal to a times b plus a plus c. All these properties means that R has two binary operations having all these properties. It leads to say that R is a field, and more particularly R equipped with plus and times is a field. Okay, so any structure having two binary operations that satisfy all these properties is called a field. You will study this in algebra, so no need to focus a lot in here on it. Now we continue to investigate the properties in R, of the numbers in R, and we will talk about the order in R. Okay, and finally we will sum up all of these properties in few words. Now, what about the order in R? Order, it means that the numbers are ordered, so you can find an order between them. And when I say order, I'm talking about a relation between the numbers that will put them in order. For example, if I take the students in the class, I will say that these students can be ordered according to the relation. For example, is younger than. It means that I can take all the elements in the class, all the students, and then put them in a row, let's say, saying that the first element is younger than the second one, the second is younger than the third one, and etc. Of course, they can be two elements can have the same age, so the relation can be younger or having the same age as. And then in this case we can put all the students, the one behind the other, in an ordered way. So the first one is the younger one, and etc. This is how we define an order. Now this order can have many properties. First, to be called an order, it should have three properties. It should be reflexive, antisymmetric, and transitive. Reflexive means that if you take an element, it should be in relation with itself. So if I take someone from the class, is he or she younger or having the same age as himself or herself? Yes, because he or she will have the same age. So the relation is reflexive. An element is in relation with itself. Is it transitive? Transitive means that if we have three elements, the first one is in relation with the second one is in relation with the third one, it means that the first one is in relation with the third one, which is the case. If student 1 is younger than student 2, or having the same age, of course, student 2 is younger or having the same age as student 3, it means that student 1 is younger or having the same age as student 3. So if we have this kind of relation between any three elements in the set, it means that the relation is transitive. So it's also true for the relation we just defined. Now, is the relation antisymmetric? Antisymmetric means that if we take two elements such that the first one is in relation with the second one, and the second one is in relation with the first one, so these two elements are the same. It means that if we take two elements from the class such that the first one is younger or having the same age as the second one, and the second one is younger or having the same age as the first one, it means that these two elements are equal. So in the class, it doesn't work because you can have two students having the same age. So the first one is in relation with the second one. The second one is in relation with the first one, but they can be two different elements, two different students. So it's not antisymmetric in this case. Okay, but if we take the relation less or equal in R, now it's reflexive because of course any two numbers are, the one is less or equal, sorry, reflexive. Any one number is less or equal than himself, of course, because it's equal to himself, to itself. It's transitive because any three numbers in R, if the first one is less or equal than the second one is less or equal than the third one, it means that the first one is less or equal than the third one. And it's antisymmetric because if you have two numbers such that the first one is less or equal than the second one, and the second one is less or equal than the first one, it means that the number is the same. Okay, so in R it works. In the relation I gave in the class, it doesn't work. So we have these three conditions, and between parentheses you will also study the order in another course, but now we should talk about it in here because we needed to put an order to the elements in R, to the real numbers. So having the three relations, the relation, these three properties, sorry, the relation is called an order. Now, we have something more. Is it a total order or a partial order? I call it a total order when any two elements in the class are related, or any two numbers in R are related. So is it true that any two students in the class, there is for sure necessarily one of them is younger or having the same age as the other one? Yes, that's true. So any two elements are related. So the relation here is a total relation, let's say. It's not an order in the case of the class. In R, it's the same case. If you take any two numbers, you will have for sure one of them is less or equal than the second one, whether it's the first then the second less or equal than the second one, or the second one less or equal than the first one. You have also one of them is in relation with the other one, which means that the order in here is total. Now you can tell me, of course, but Mr. It will be always a total order. That's not true, because let's say in the class, if I take the relation is having the same age or younger, and of he's or she's of the same sex as the other student. It means that I can compare only two elements if they are both boys or both girls. I cannot say a boy is younger than a girl. They should be of the same sex, and then I can compare their age. In this way, you will have all the boys ordered one younger than the other one, and etc., and all the girls ordered together, and then you will not have a total order. Not any two elements of the class can be related in this relation I defined. This way, the order, of course, in the class we said it was not an order, but if it was an order, the order in this case we call it partial and not a total order. Now, what interests us in our case is the set of real numbers R. In R, we have a total order for the relation less or equal, okay? Which is a very nice thing because we will be able to order all the numbers in R. So the numbers in R, that's why they will be ordered on a straight line where you put 0 and then you put all the numbers, the one after the other one. Okay, so you can order all the numbers on a straight line or on an axis. Okay, watch out that, for example, because you know already the complex numbers from last year, you cannot define an order easily between the complex numbers, right? What does it mean to say that a complex number is less than the another complex number? It's a plus ib. If you take, for example, 1 plus 4i and 2 plus, let's say 0.5 plus 2i, is this one less or equal to this one? We don't know. It depends how you define less or equal. If you define less or equal as being you have the real part less than the real part and the imaginary part less than the imaginary part, that would be yes, they are related. But what about these two numbers, for example, 2 plus 2i? This one and the first one in here, they are not related because you have the real part greater than the real part and the imaginary part less than the imaginary part. So they are not related. So the order you just defined cannot be applied between any two elements. Okay, anyway, so this is the idea. And so we say here that the order is total if any two elements for all A, B, and R, so any two elements you choose in R, you have whether A less or equal to B or B less or equal to A for sure. There is one element that is in relation with the other element. Of course, we will denote by less strictly like this without the equal. If the relation is strict, it means that A is different than B. We say that also B is greater than A. It means that A is less or equal to B. It's the same order, but in the other way around. And we say also that it's greater strictly if B is different than A. So to sum up, we will say that the real number set is a commutative. There is something missing in the PDF here, so I will add it. Is a commutative, totally ordered field. So commutative because times is commutative. Totally ordered, we explain what is it, and field because it has all the properties for plus or minus. Now, of course, the order that we defined can be used also together with the binary operations. Means that if we take two numbers that are in relation, anyway, any two numbers in R are in relation less or equal. So if I take two numbers A and B such that A is less or equal than B, then you can add a number C to both of them and the relation is conserved. Also, if you take two numbers X and Y, X less than Y and A less than B, it means that if you add X to A and Y to B, you will have the same sense for the relation. X plus A will be also always less or equal to Y plus B. If you take three numbers A, B, C, having A less or equal to B and C is positive, you can multiply both sides by C and you'll have always the less or equal in the same direction. So AC is less or equal to B. Now, R, we said that it's the set that contains all the real numbers. Okay, that are numbers that can be written as integers, numbers that can be written as rational numbers, numbers that are decimal with terminating or decimal non-terminating periodic or decimal non-terminating non-periodic. All these numbers are real numbers and they can increase as much as you want. But the thing is that we will add to this set two elements which are plus infinity and minus infinity, which are two elements that are not exactly real numbers, but it's an element that is greater. Plus infinity is an element that is greater than all the real numbers. So it's not a real number, because if it was a real number, you just add one to it and you will have a real number greater than this number. So plus infinity is considered as an element that is greater than all the real numbers, and minus infinity is an element that is less than all the real numbers. And this new set would be called R bar, while the first one in here was R. Okay, why do we add these sets? Because these two elements, because will be now when I say R bar, it's somehow a notation. When I say R bar, I mean all the real numbers and two additional elements which are minus infinity and plus infinity. This is what I call the extended real number line. because we already defined the order in R, so all the elements in R are defined on a line. And now it's the extended where we add plus infinity and minus infinity. So R bar will be the set R reunion or union two elements. This is a set that contains two elements, minus infinity and plus infinity. So defining these two elements, we will extend the binary operations and the order from R to these two elements. So we'll say that we can add an element x plus plus infinity, it will give plus infinity. So it means that this number will always remain, if you add something to it, it will always remain something bigger than all the elements. And if you add x to minus infinity, it will be minus infinity. If you multiply x by plus infinity, it will be plus infinity if x is positive, and it will be minus infinity if x is negative. And if you multiply x by minus infinity, it will be minus infinity if x is positive, and plus infinity if x is negative. Now, if you add plus infinity to each other, it will give plus infinity, and minus infinity to each other will give minus infinity, and multiplication will be dealt with as two normal numbers, so the sign will be positive if they have the same sign, and negative if they have opposite signs. And of course, minus infinity will be less or equal than minus infinity, and plus infinity less or equal than plus infinity. So these properties, we are defining them, so we are considering that they are true, so we can compare the numbers with the infinities. Okay, and of course we have some forms that we don't know, that are not determined, they don't have an answer, that are the plus infinity plus minus infinity, or minus infinity plus plus infinity, 0 times n infinity, whether it's minus or plus. Okay, so this is what we call the extended real line. Since I talked a bit about a line, before going to the next section, let me point out some remarks. In fact, the thing is that if we take the axis where we will put all the real numbers, the real numbers mean it's the integers, the rationals, the irrationals, everybody. Let me consider first the integers. The integers, you have them at very defined positions. So 0 is here, 1 is here, 2 is here. And between 0 and 1, you have no integers. Between 1 and 2, you have no integers. And also you have -1 here, -2 here. Now, if you put the rational numbers, you will have them everywhere. So if you put, let's say, for example, 1 in here, this is a rational number, and 0 is a rational number, belongs to Q and belongs to Q. Okay, you can always find the ratio of these two numbers. I will take, let me take again 1 and 2, for example. It's more practical. I will take 1 and 2. This is a rational number, and this is a rational number. So you can always find the average of both numbers, which is 1 plus 2, 3 over 2. 3 over 2 will be between them. This is 3 over 2, which is a rational number also. Okay, and then between 1 and 3 over 2, you can always find also a rational number that can be, for example, the average of both 1 plus 3 over 2 over 2. It will be inside. And then between 1 and this average, you can find a rational number. So rational numbers, you have an infinite number of rational numbers. Between any two rational numbers, you can find a rational number. And also, between any real numbers, you can find a real number, of course, because they can be rational. And also between any two irrational numbers, you can find an irrational number. Let me point out this structure where between any two elements, you can find an element, which is very important to the notion of limits that we will be considering in the next chapters. Okay, so it's very important to notice this issue or this property, but also I will give you something to look about on the internet. Search for the countability of Q. We say that Q is countable, and the non-countability of R. We say that R is not countable. This is something, an extension to what we are doing here. I want you to look for it on the internet to see that Q is countable and R is not countable. Look for it, search what does it mean and why it's true or not. So this is for only for your own information. It's a very nice topic and interesting idea and interesting difference between Q and R.